Today, we will focus on something more sophisticated than just when to use the different types of databases. Managing stringent performance requirements for distributed applications almost always involve a combination of systems design building blocks that are tactically integrated. These are known as distributed design patterns. They are prescriptive guidance on how to design for specific performance challenges. The exact implementation may vary depending on the cloud service provider you are with and the actual application you are implementing. I will take you through a few of these patterns to illustrate how to understand them and also apply them to specific scenarios. Let's revisit the Caffe operating system that we have been designing together. In the very last video, we've completed a basic round of performance design using just very simple systems design options. Now, let's add some performance requirements to this and let's see how we can meet them with distributed design patterns and why we need them. Since we're splitting the application into various services for behavior design, so we first need to manage the integration complexity. Since there is a rather linear workflow in our simple ordering process involving multiple steps, we need an effective way to manage the procedural execution among different services. For example, after placing the coffee order, the user should be asked to pay for the coffee via the payment backend service. And only then, the order is confirmed for fulfillment. However, if the payment fails for some reason, the order should be cancelled. We need to properly manage these transactions. And we can hardcode this if all these business logics are packaged and deployed together. But that wouldn't help our solution to be adaptable and maintainable. With the distributed nature of the design, there are two ways we can manage these transactions, with either a centralized orchestration pattern or a distributed choreography. Orchestration, the centralized approach, is much like having a conductor in a symphony. There is a central entity acting as a state machine that coordinates with the services involved based on the state of the transaction in the predefined processes. The orchestrator handles the state of the transaction and navigates the path forward based on the outcome at each step. The benefits of this approach is decentralization. You have all the executions being managed in one place, hence it is easy to recover from errors or to debug the application. On the other hand, choreography is completely distributed. Every service may have queues that are waiting for new transactions, and depending on the outcome of the current step, they are being sent to another service queue. This allows a little bit more flexibility and loose coupling, but less transparent and higher operational overheads. In these scenarios, when something goes wrong, you will smell the smoke, but you won't see the fire until you individually verified the logs from the services involved, and that tends to be a lot of work. Next, let's also add a high-performing loyalty points system for our cafe. Our customers can earn points with each purchase, and points have an expiry date. Points can be redeemed to offset costs of future purchases, so we must create a system where we can manage the lifecycle of groups of points that our customers earn. We should be able to create a report quickly for each customer should they want to know how many points they have in the profile. The naive solution is to put every group of points into a relational database, and every time a customer checks for the amount of available points, do a select and filter by date. The write operations will be relatively quick, but the read operations, whenever one wants to check the available points balance or to use these points for purchases, is going to be a bottleneck. We definitely don't want people waiting at a checkout counter just so our system could load. What if we use a different data structure for read and write operations? Let's prepare the points balance for each user beforehand on a schedule, so read query time will be blazing fast this time. We can also store the point-in-time snapshots of each user's points balance in a document, instead of using rows in a relational database. As for the write operations, such as adding and redeeming points, we might as well separate it into a different relational database too. This way, We can separately scale this service for reading and writing for the loyalty point system. This is called the Command Query Responsibility Segregation, or CQRS, where we use different data structure and persistence methods to maximize the performance for read and write operations separately. The schedule update process to compile the read operation items to prepare a snapshot for the read operations is called a projection engine. We're not just quite done yet. As our cafe becomes more popular and the customer base grows steadily, we need our system to be more reliable in times of unexpected disruptions. If we adopt an event-driven approach to the integration, then we can also apply the event sourcing pattern to make our systems more resilient. The idea is very simple. We keep appending new events that allow us to construct a point-in-time view of the overall state of the system. Say we want to keep track of the total number of coffee orders at any point in time. Instead of incrementing the total number of coffee orders we got, we will store each order as a separate entry with its own timestamp. So in the case of a disruption, we can reconstruct the total number of orders received from the individual order entries. But will this restoration process become exponentially less efficient as there are more and more tally as more events are being stored? That's why we want to take periodic snapshots as checkpoints and flush the individual event records. This can be utilized in each microservice to maintain its own state consistency within its bounded contexts. These design patterns should ideally not be your first solution to improve the performance requirement because of the additional complexity that they introduce. Perhaps the peak traffic level for your application doesn't require a full CQRS implementation to achieve the low read latency. You might just need a more robust caching option or a database replica. Today, there are a lot of managed cloud services where a lot of these functionalities are at least partially available. If there is an infrastructure deployment option that can meet your current performance requirement, then go with the simpler design for now. Just remember the trade-offs you're making and plan for the time when the performance degrades again and we come back to the design board. As long as you follow the high cohesion and loose coupling principles, your software system should stay adaptive enough for you to easily switch to a more elaborate solution later on. As you can see, these distributed design patterns don't just help us satisfy performance requirements. They do also help to enable certain behaviors that would otherwise be difficult to model. If you haven't heard of these patterns before but have been developing for a while, you most likely have already unknowingly implemented some of this. The best part about these patterns is that they are well documented and you don't need to distill these technical solutions from scratch every time. So you should definitely read up a little bit more on the other patterns to know what you can refer to when you have a performance challenge next time. I will leave some of these materials in the description for you to check out later. With the incremental design for adaptability, I hope we can avoid major overhauls. But inevitably, at some point in time, the software system will need an upgrade that poses significant risk for disruption. It's what happens when we finally need to change what's been working so far, and Murphy's Law does not spare any project. In the next video, we will discuss how to handle major changes to reduce the impact radius and to avoid expensive disruptions. This is crucial if you want to build complex solutions and scalable systems. My name is Derick Chen. Thanks for watching, and I'll see you in the next video.